the speed of the light is highest in vacuum or in air. So somehow if you can create an optical communication channel where the light is traveling into air, it will give you the low latency. So yeah, somebody is saying something? Yeah, okay. So if you have a question, you can stop me. Otherwise, I can take the questions at later stage. So we can have the low latency when it can go into the air. How we can make the such a medium? So using the photonic crystal fibers, we can propagate light into the air because that fiber has the core, which is basically air. However, the scattering effect will still be there. Since scattering is there, so normally it is a Rayleigh scattering, which is lambda raised to the power -4. If we can go for the higher wavelength, we can have high speed as well as the low loss. And if we are increasing the wavelength, let's say we are going from 1550 to 2000 nanometer, the loss will be low. Okay, and not only the fiber, we also need the amplifier. So luckily at this wavelength, we also have the amplifiers available. Therefore, there is a perfect case for going to the 2 micron communication window in the future. So we are doing some work at 1550 nanometer as well as we are doing some work at 2 micron. So that is why I introduced these optical communication windows, and here is a reason why we should go for the next communication window. However, commercial reasons may not allow us to go immediately to that, but if we want low latency and low loss, then there is no option, but we have to go further. So this talk is focused for 1550 as well as for 2 micron. Okay, so in case of optical communication window around 2 micron, we already have the fibers and we have the thulium doped amplifiers. So here are some examples that I have taken. So this is even commercially available. So this is a company from where you can buy a 2 micron fiber. Okay, and this is again from another company, Coherent, from where you can buy this thulium doped fiber amplifier. And at research level also a lot of things are going on. So not only the thulium, but you can have other materials like holmium, etc. for the amplification in the communication window that is around 2 micron or even beyond. Okay, so here is a nice experiment by ORC group where they have holmium doped fiber amplifier for optical communication beyond 2 micron. We have all these things. Okay, but if we think deeply, what are the things that we need? We need switching, modulation, routing, and also the signal processing. Okay, so having a fiber and the amplifier is good. We can have the detectors also, but there are many more that we need. Okay, other major question is we need to be cost effective. We need to be energy efficient. Okay, so if there is no economic viability, nobody buys your products. And if we can use the monolithic platform, okay, so we can fabricate many devices in a single go. Okay, however, we don't want to use a platform which doesn't have a proven track record of being good. So we are looking for a platform that has a proven track record. Okay, so silicon photonic platform has been proved at 1550 nanometer. So there is a huge potential that it will be very good for 2 micron also. Okay, and if we can do the silicon photonics, we can definitely do the hybrid silicon photonics, bringing in more materials. Now let's come back to the phase change material. Okay, so this is basic. When I say the phase change material, it is basically a structural phase change material. So you can change the phase from amorphous to crystalline and vice versa. Okay, so this you can do by heating. Heating can be electrical or it can be optical. You can send the optical pulses and heat it, or you can supply the current. You can apply a voltage where the current will flow, and because of Joule heating, the heating will be there. Okay, so the important thing to note about here is, if you are looking for the resistance change from here to here, is huge. It can be 1000 times. At the same time, there is change in the resistivity, reflectivity, absorption, etc. So we are mostly concerned about the transmission. Okay. So if you are going from here to here, there is huge and drastic change in the refractive index, which gives the change in the transmission, and that we can exploit for making the switches. So The refractive index contrast can be as high as 2.58. It is really huge. You cannot have normally any other material which can give this kind of refractive index. If you are looking at 1550 nanometer, 4.67 versus 7.25 in the same material, okay, which you can also switch from crystalline to amorphous and vice versa. Okay. The beauty of this material is it not only gives the refractive index change in the real part, but it also gives the refractive index change in the imaginary part, 0.12 to 1.49. This is also huge. And luckily at 2 micron also, the same material can again give the high refractive index contrast. So we can do the devices at 1550 nanometer as well as for the 2 micron. Okay. And the material GST, Ge2sp2Te5 we are talking, it has a proven track record. It has been used in non-volatile electronic memory technology for many decades. It is compatible with the CMOS fabrication process. Also, the write and access time are very high. They can be like 10 nanosecond and 100 nanosecond in electronic domain. In optical domain, they are likely to be faster. We are talking about the phase change switch. So what are the properties we are looking for a phase change switch? We want optical, because now we are photonic switch. So I will talk only about the optical parameters. So we need the optical contrast as high as possible, that you can obtain by change in the extinction coefficient, which is imaginary part of the refractive index, or the refractive index, which is basically the real part of the refractive index. So depends what kind of effect we want, but both we can exploit. Okay, optical loss, so it's mainly an insertion loss. Okay, so it should be as low as possible. So this material in amorphous phase is less lossy, and in the on state it will show very less loss. Now the switching speed, sub nanosecond is possible. Further investigations are required if we want to go for picosecond or so. So nanoseconds or sub nanoseconds can already give you a gigahertz speed or even more. Okay. Other property that we always look for is the compatibility with the standard fabrication process, which is there. So not only silicon is compatible with the CMOS fabrication process, the new material that we are introducing, which is a phase change material, is also CMOS compatible. And we can make the CMOS compatible switches using this material. Now let's go a little bit into the theory, how these devices, etc. work. Dr. Balraj, am I audible still there? Hello?
Yes.
Okay, good. So time to time I will keep checking because of the net connectivity since I'm on mobile. So how all this works? Okay, so if we go for the basic physical science theory, you all know that if we have a ground state and we have an excited state, okay, even in E2, this is a two-level system. When a photon is incident, so it will take the atom into the higher state. So this photon is basically absorbed by this atom. So this radiation is basically now attenuated. Where the radiation is gone, the radiation is basically gone into this atom, and this atom now attains the higher excited state. Okay, so this will give you the loss or the attenuation, and we will deal more with it in the coming slides. And there are other processes like spontaneous emission, which gives you the light out. You can also have the stimulated emission, where you have one incident photon and you have the radiation which is coherent. However, today we are not concerned about it. We are concerned today with the simplistic treatment, how the atom gets excited when it sees a photon. So I will give the semi-classical theory of the same. Now let's assume that we have an optical beam of a particular wavelength and that is incident on some medium. And assume also that the electric field of the optical wave, it is E equals to E naught exponential I omega t. Okay, so you see the T term. So this is basically an oscillating field. Okay, so all charged particles in the atom will feel this electric field and they will oscillate either up and down or forth and back. Okay, depending upon the direction from which the light is coming. Okay, so this is a kind of harmonic oscillation, back and forth, up or down. Okay, now these atoms also have the dissipation problem. Okay, so if we write the complete equation, then this becomes a case of driven damped harmonic oscillator. Okay, so This is very much known equation to everyone, whether you are from physics or electronics. I'm sure you have come across the damp-driven harmonic oscillators at some stage, where the symbols have usual meaning. M is the mass, X is the position of electron with respect to atom, gamma is important, it is a damping coefficient, and omega naught is the resonant frequency. How you can associate this resonant frequency with the energy levels? We all know delta E is H cross omega, where delta E is basically nothing but the difference of these two energy levels. Now the solution of this equation you can do step by step and you can arrive at this. And you can substitute for E from the previous slide and you will have this equation. Okay. We also know about the induced dipole moment, that is P equals to minus EX, and X we have obtained, that we can substitute here. I wish I had a board to write, then it would have been much nicer, but you can see and it is understandable. We also have the P equals to alpha I. Alpha is the polarizability of the atoms or the molecules. So alpha you can write like this. Now refractive index is associated with susceptibility, n square equals to 1 plus chi, and chi you can write as n alpha upon epsilon naught. So here you see n is basically associated now with alpha and n, capital N. This capital N is the number of atoms per unit volume, and this is the reason basically solids have higher refractive index compared to the liquid or the air, because n is much higher in solid as compared to liquid and air. Okay. So if you substitute here, you can see this basically has something with iota. Okay, so this is important. Okay, now when we have omega equals to omega naught, okay, chi by virtue of substitution, you can have it like this. Okay, so here if you see chi is now purely imaginary. Okay, when we talk of the complex numbers, okay, so what is complex about them? There is nothing complex. Actually, a plus ib, so b is only showing the loss. That is the important thing to note about. Okay, when there is no, when in a complex number c equals to a plus ib, when a is not there, only b is there, that means that number is representing something which is basically lossy. So likewise here, you can see there is no real part anymore. It's purely imaginary. Okay. So when something is purely imaginary, it is a completely a lossy system. Okay, so this means system is lossy. So where the radiation is going, the radiation is getting absorbed by the atom. So this is mathematically also we are convinced, and from the energy level pictures also we are convinced that the systems can be lossy. Further from there you can do manipulation, etc. So idea here is to show that sorry, the effective index, it is having the real part as well as the imaginary part. So imaginary part is called the extinction coefficient, and it can be given like this, which is again dependent upon the number of atoms you can see and gamma, and also the resonance frequency, etc. Okay, so this you can associate practically with the wavelength, etc. also. That is what we are going to do. Okay, so this is good. This is a fundamental constant. However, it is difficult to measure. You can use the ellipsometry, but there are easier methods, and how to go for them to measure this coefficient I'm going to show in the derivation. Okay, now assume that there is a monochromatic wave that is propagating in the medium, and the medium is now complex. When I say the medium is complex, means it is having a complex refractive index that is given by n minus I kappa. Okay, and E equals to a exponential I omega t minus this k prime z, where k prime is the wave number in the complex medium. If you substitute, then you can find out this k prime can be written as 2 pi upon lambda n minus I kappa. Okay, where k is the extinction coefficient or the imaginary part of the refractive index. Now you can substitute here, you can get this value. Now you pay attention to this exponential minus 2 pi upon lambda kappa z. Okay, so this is what we are going to use further. Okay, so intensity you can write as being proportional to E dot E star. When a light is propagating and it is covering certain distance, its intensity will be attenuated like di upon dz equals to alpha I, and you can write the solution of this I equals to I naught exponential minus alpha z. Okay, where alpha is basically the attenuation constant. Now from the previous slide we can substitute E and E star, and you will see this term which I was mentioning is here in the E, and it's also present in the E star. So the total decay term for the intensity is exponential of minus 4 pi upon lambda into kappa g. Okay, now if you compare this and this, you will have alpha equals to 4 pi upon lambda into kappa. Okay, now alpha is associated with the kappa. Okay, so alpha is attenuation coefficient and kappa is the extinction coefficient. So if you can vary this kappa, the alpha will be varied. So this relation is very widely used for loss calculation, and it is important for the attenuation based switches. Okay, so this is the theory I wanted to cover, because you should be now convinced by changing the imaginary part of the refractive index how we can obtain the switching, because this is the loss. Okay, so let's say it was some kappa 1, it will be alpha 1. If it was kappa 2, it was alpha 2. So the difference in the loss, it will give you the switching functionality. State of the art about these phase change switches. So people have been investigating it for a long time, around 2015 or so. It's not that long, but still there were some papers even from 2012 or so. But it's very relatively new field. Okay, 9 or 10 years is nothing in the research field. So most of the time, what they have been doing, they have been integrating GST on top of the material, that is silicon here. You can see. Okay, and this does not give the optimum performance because there is evanescent interaction, and because of evanescent interaction, you can simulate it and you will find out this will give the limited extinction ratio at the most 10 dB. 10 dB is also higher side. Also in this case, they have been having the large size GST, which is difficult to switch. When you are switching from amorphous to crystalline and vice versa, some part of the phase, some part of the material is not phase changed. Okay. Then there is an example where people try to embed the GST into the silicon waveguide. However, this way the fabrication becomes very difficult. So clearly there is a need to have the enhanced interaction of radiation with the matter. Okay, so there are 3 cases that I have indicated here. You can have it on top, you can completely embed into it, you can partially embed into it. So each of these have their own advantages and disadvantages. So after running simulation, etc., we found out that this gives the best performance. However, it is a bit more difficult to fabricate, okay, as compared to these two. But it gives the high extinction ratio and low insertion loss. So here in this case there is low extinction ratio and there is high insertion loss. What we want reverse actually. We want low insertion loss and high extinction ratio. So this situation permits us. You might be wondering about this yellow portion. So this is nothing but ITO, which is a transparent material for having the electrodes. Okay. So we have been doing in-depth study of this and I'm going to show some results here. Okay. So here again, this is a representation how basically we design. Okay, so at the heart of this is basically change in the alpha by virtue of changing kappa, extinction coefficient. The rest is basically mathematics, how the light etc. is confined. Okay. There are 2 ways, as I mentioned in the beginning itself, of switching this. One is optical, another is electrical. So in case of the optical, light gets absorbed and it gives heating. Okay, so this is basically a heat equation that we solve. So here this K is basically electrical conductivity. This is change in the temperature. This Q represents the source term for the heat, and this is specific heat, and capital T is the temperature. In this case here, again the same equation we are solving. However, now the source term for the heat is different than this. It is a joule heating. Okay, Q equals to sigma E square and J equals to sigma E. They are similar but still different. So for change from amorphous to crystalline form, we need a bigger pulse. For change from crystalline to amorphous phase back, we need shorter pulse. So this is basically a melt quenching process. And typical times, so this is the T2 time, which is around 10 nanosecond, and this is 100 nanosecond. This is standard we have taken from the literature. Okay, more investigations are on to find out what can be the best time. Okay, so in order to change the phase, we need to change the temperature. So if you are at room temperature, you need to go to 140 degrees Celsius for change from amorphous to crystalline. And if you want to come back from crystalline to amorphous, you have to go to the temperature which are beyond 500 degrees Celsius. However, there are some demonstration where you can do around even 500 degrees Celsius. So this is the design how we do. So this is, you take the silicon on insulator waveguide, you fill in the GST material, then you look at the transmission curves. Okay, so here you will see this gives the switching functionality. However, the maximum extinction ratio that you can get is around 34, but it comes at the cost of high insertion loss. This insertion loss is not acceptable for the practical application. However, the concept works, but it's not really good for the practical applications. Then there is another case where you can yeah, please.
Sir, I want to know in practical applications, what is the extension ratio generally you prefer?
Normally it should be around 0. I mean, definitely it should be less than 1 dB. Okay, and people prefer like 0.3 dB, 0.4 dB, 0.5 dB depending upon the applications. Okay, actually in the end you have to make a power budget, and if it is around 0.5 you are good enough. Okay, even 1 will work, but 3 dB means like 50% of the light lost just as an insertion loss. Okay, so you don't want to go for that. In the previous case, you see this is 4.33. Okay, so it is even more than 50%.
If we talk about optical modulation, yes. Then what is the range for extension ratio in fabricating that modulator?
So first of all, the extinction ratio, it comes from the, when you measure. No, this doesn't come from the fabrication itself. Okay, now when you do modulation, so there actually you want higher speed, okay, and high extinction ratio. So the extinction ratio that you need for the long haul communication should be bare minimum of 10 dB. However, 30 dB or 45 dB, 50 dB, that is like preferred range nowadays. If you're talking of on-chip communication, okay, for a short range, for limited number of devices, you're fine less than 10 dB. Okay, but these ranges, if you set them lower, you pay the penalty in some other form. Okay, bit error rate, etc. are basically linked to your initial extinction ratio. Okay, when it goes through the channel, okay, the 10 dB extinction ratio is hard to maintain because the noise will be added. So if you have higher, let's say 40 dB or 50 dB, by the time it reaches the receiver, okay, you have good enough extinction ratio even if it is degraded. If let's say 10 dB degradation is there, 50 will become 40, but the 10 dB will become 0.
Okay, then we won't be able to differentiate between 0 and 1.
Yes. Right. So the thing is, yeah, so you would like basically, bare minimum of 10. And as I told you, this is also quite specific to the kind of circuit that you are using. For long haul communication, now 30 dB is like something people are easily doing. Okay. And 10 dB was a time, let's say 1960s or so. But now we need 30 dB or more. Okay. Should I go ahead or you have more questions?
No, sir.
Oh,
thanks.
Okay. Right. So now here we did another simulation where we can find out that we can go up till 50 dB of extinction ratio. Okay, and insertion loss is still high, around 3.25. Again, it's more than 50% of the light is lost. And this also gives the additional problem that I'm summarizing next here in these two slides. So for these two approaches, you can get the extinction ratio, which is good enough. However, the insertion loss is not acceptable. Okay, and in this case, if you are putting the electrodes, of course, it will interfere directly with the light. It will give additional loss. Even here, it will give some additional loss, but that may be minimum because the electrode will be on top. So it will see only the evanescent tail of the light. So because the insertion losses are unacceptable, we are going for another case, which is partially etched case. Okay, so in this case, here by varying the dimensions of GST and at what position you are filling the portion of the silicon, you can get extinction ratio of more than 40 dB with insertion loss of around 2.76 dB. However, if you can live with the 10 dB, then this insertion loss comes out about 1.2 dB. Okay, so we have further simulations where we used certain concepts of directional coupler, where we found out the insertion loss of around 0.3 or 0.4 dB, which is unfortunately not here in the slides today. Okay, so that is a photonics research paper from our group. You can see which is there. So in today I didn't put it because I wanted to start from the beginning. Okay, so 0.4 or 0.3 dB is possible. Okay, so now if you look at the spectral response of this switch, it is maintaining the high extinction ratio of more than 30 dB in a very broad range, 1500 nanometer to 1600 nanometer. And here are the field profiles, which is clearly indicating the switching functionality using this kind of devices. So for all optical switching, you have a pump probe experiment that you can do, and you can see how the phase is changing. Okay, so with a pump power of around 1.6 milliwatt or so, you can obtain a temperature of around 140 degrees Celsius. However, a little bit portion is left. Okay, you can do the complete phase transformation, but the temperature reaches so high that it becomes difficult that how to save other material in the vicinity. That's why you leave some portion unchanged, and you have the extinction ratio which is good enough with optical pump power of 1.6 milliwatt. Okay. Likewise, you can do the reverse switching where you need more power because you need to attain the high temperature. Okay, around 400 degrees Celsius or so. Again, some portion is left. Okay, but it is good enough for high extinction ratio. Now, that was the electrical switching. Sorry, optical switching. You can do electrical switching, which is based on the Joule heating. You have the electrodes, which are made of ITO. We are choosing ITO because they are optically transparent and electrically conductive. Okay, so with a voltage of 2.5 volt, you can do the phase transformation from amorphous to crystalline. However, from crystalline to amorphous, you will need a little bit more, that is 3 volt pulse. And these diagrams are basically showing the phase changes happening now into the complete material. So that was work for 1550 nanometer. Now we are at 2.1 micron. So since we are going from 1.55 micron to 2.1 micron, the cross section of the silicon waveguide will also be changed. Okay. In previous case, we had 450 nanometer wide and 220 nanometer high waveguide. Here you can see these dimensions are higher. Now we are having 800 nanometer width and 400 nanometer height. So this is good enough for supporting the single mode operation at 2.1 micron. Okay. So here there are two approaches, GST in fully etched and GST in partially etched case. So in case of fully etched, okay, we run the simulations again and we are finding out that we can have the low insertion ratio, but the 14 dB extinction ratio is something that we don't prefer. This is okay, but we can do it better. Okay, so here you will see we also observe the negative extinction ratio. This means there is more light transmission in case of the crystalline, which is peculiar. Normally crystalline should be absorbing more. However, there is a mode which is less confined in case of the amorphous and more confined in case of the crystalline. Okay, so this is how this negative extinction ratio is observed, that you can see here. This is an interesting observation that extinction ratio can even be negative. With the another case of partially etched, which is expected that we will have better extinction ratio. So we are having more than 30 dB, 30 dB, that is 34 here, and now the insertion loss is less than 0.5 dB. Okay, and if you can further live with lesser extinction ratio, this can come further down. Okay, so at 2.1 micron, they give really a high performance. So in both cases here, I'm showing the profiles, and this works as a switch for the fully etched as well as for the partially etched case. Again, like we did for 1550 nanometer, we are at 2.1 micron also. We can switch the material completely by applying the voltages. So here we have 5 volt for amorphous to crystallization and 100 nanosecond pulse duration. So if you observe this and this, in both cases, this is completely phase transformed. Okay. However, with optically it is difficult because the light has certain mode and it does not basically uniformly heat the material. Another switch that we realize is directional coupled switch. So here is some basic theory, so which is based on the evanescent coupling of light from one waveguide to another. There is periodic exchange of power from one waveguide to another. So you can launch light here, you can get it here, but under certain condition you can bring it here. So that depends upon the interaction length or the coupling region. Okay, how long is the coupling region? Based on that, you can have the light output here or here. Okay, when it goes straight, then we call the bar, and when it crosses to another output, then this is called the cross state. And there are parameters such as the contrast ratio, insertion loss, that you have to look for these kind of switches also. Okay, so in our case, we have embedded GST in one arm of the waveguide. Okay, and so what will happen if you look at this figure? Okay, when it is in crystal form, the light goes just straight. When it is in amorphous form, it basically couples into it. Okay, so by changing the phase, you can switch whether you want to be here or here. Okay, so whether the light should be here or here. So this is the directional coupler working as usually it works for the fiber based directional couplers also. Okay, so this all we have done by having the GST embedded into the silicon waveguide material. So again, for the sake of completeness, I am showing here the complete phase transformation is possible. Okay. Now, another topic that I want to cover is about the reconfigurability. I think I need to be a little bit faster now. So we need reconfigurability because it allows you the operational flexibility. And whenever you fabricate some device, there are certain detrimental consequences that are happening there. Okay. So when you go for fabrication, and if you want to fabricate the same way as you designed, it's just not possible. Okay, so fabrication process induces certain errors. So you can overcome those consequences of the fabrication process if it is reconfigurable. Okay, and you can adapt your circuit or device to a particular environment, particularly in a country like India. If you are, let's say, in Pori, and if you need to go to Rajasthan where the temperature is high, okay, the performance will change. Okay, but you don't need to worry if your device is reconfigurable. And other reasons come from the fact that we want everything to be compact, so it saves space and it is cost effective. Okay, because if you have reconfigurable devices, many functionalities, or you can operate it at many wavelengths. Okay, so that means if you want to operate at 10 wavelengths without reconfigurability, you need to have 10 devices. With reconfigurability, just one device can do. So it will save space, it will give you the cost effectiveness also. Okay, and constant power, that is always a question. So our material, this is non-volatile and is also basically stable at multiple states. Okay, so therefore there is a case of having the reconfigurable device with this material. Okay, so we are mainly using the micro ring resonator. What is micro ring resonator? That I want to introduce a little bit. So normally if you have two mirrors, okay, the light is there, it bounces forth and back, and if you have a certain length, okay, such that the round trip phase shift is basically 0, then you can have a resonator, which is popularly known as Fabry-Perot resonator. What if you can adjust these mirrors such that the light travels in a ring form? Okay, so then it becomes a ring resonator. So this is a bulk arrangement. For the integrated platform, we just make a ring in silicon, we put the access waveguides here and here. Okay, so this is your input, this is through, and this is your drop, this is your add. Okay, so basically what you see here is the copy of this. But this is a bulk arrangement and this is your integrated silicon platform. So the light will couple when the light will resonate when the resonance condition is satisfied. That means the optical path length, that should be equal to the integer multiple of a wavelength that we are using. Okay, so optical path is basically your physical path multiplied by the refractive index. So 2 pi r multiplied by the refractive index. So this is the condition that you need to satisfy for obtaining resonance. And here is basically formula for the transmission at the through port and drop port. Okay, so I will not read out, but what is important is basically the this factor a equals to exponential minus alpha 2 pi r. Okay, so this gives the round trip loss, and phi. Okay, that is the phase, which is beta L, and then beta you can write as 2 pi n effective upon lambda multiplied by L, and you can further solve it for 4 pi square n effective r upon lambda. So these two are important factors in these equations. Okay, so you have to look for the phase as well as the round trip loss. This is what we did. So we have a micro ring resonator. In a small portion of the circumference, we are putting ITO as electrode and GST as an active material, which is very thin, like 20 nanometer. If you look from the top, it will look like this also. I assume with these two figures, you can imagine how these devices will look like. Okay, this is a very compact device. We have 5 micron radius. Okay, and we can use the thermo-optic coefficient of amorphous phase for tuning the resonance wavelength. Okay, again, there are certain relevant expressions that I will skip here because I have already explained if you are changing the loss, you can have the switching functionality. The important thing to note about the amorphous GST is it is having a thermo-optic coefficient which is 1 order magnitude higher than silicon, and that is why we should be heating prominently the GST rather than silicon. You can do with the silicon, but it will not be very energy efficient. Okay, so in case of hybrid section where GST is there and silicon is there, the heating will mainly come from the amorphous phase of the GST. So this is a typical workflow. You apply the voltage, the current will be there, and this current will cause the rising temperature, and which will cause the wavelength shift, which is basically a reconfiguration phenomena, and you repeat it. Okay. So if you are looking at the simulated results, you can see here we are having a GST, that means amorphous GST here. So light is coupling, and it is dropping out here. However, in case of the crystalline GST, okay, the light is coupling, but it gets lost here. Nothing is here. Okay, so if you are looking at this port or at this port, okay, in two cases you will find the transmission difference is there. Here transmission is low, however this is high, and the reverse is true. Here it is high and there is nothing here. Okay, and this is all because in amorphous phase the resonance condition is satisfied. In crystalline case it is not satisfied. So here are these results through port and drop port. So you can see the extinction ratios that we are having, and this is basically a micro ring resonator. Okay, it's a resonant device. So we have the extinction ratios up till 25 dB at drop port. Okay, however at the through port we are having around 20 dB or so. Okay, insertion loss is high. So this insertion loss, because the light directly sees it, if you can somehow shift this material to this side, this will become lower. Okay, and that is what we have done in another paper, which we are not showing here. So if you want to do the phase change, again you have to apply the heat by means of electrical or optical. Okay, so here also you can do the same thing as I have been talking for the previous slides. The one important observation that we find out here, if the material is embedded into the silicon, this active material GST embedded into the silicon, the heat is very much confined to very small portion. Okay, and that also happens for the reverse phase change. Okay. So for low crosstalk circuits, we can use this material. Okay, and here these graphs, they show the temperature rise versus temperature. So you can see the rise is fast and the fall time is slower. So overall speed of operation, it will be decided by the fall times. And here are the tuning characteristic curves, which is reconfigurability. We have taken different lengths of GST, and in all cases you can see the wavelength is shifting as we are applying the voltage. Maximum resonance wavelength we have found out is around 4.63 nanometer, that is shifting. Okay, and the maximum length for this is around 7 micron. Okay, so we see a trade-off between the resonance wavelength and the extinction ratio. The good thing that we found out with our devices, in fact it's the best thing, that the tuning efficiency is best for the reported devices so far. Okay, any micro ring based devices, okay, is not as efficient as we have for the tuning purpose. Okay, so this is 1.16 nanometer per milliwatt. This is an impressive figure. So we have talked about the state waveguide switches, ring resonator based switches. So this is how the road ahead looks. You can have the complex photonic integrated circuits. Okay, so this is where you can have many wavelengths coming in. You can basically couple to different resonators. Okay, you can separate them out. Then in between you also have the phase tuning element, photodetectors, couplers, where you can manipulate their path. Okay, so you are having in one go all the wavelengths, and you are having the separate wavelengths at separate channels. Okay, so this is one example. You can make more complicated circuits. You can make a switch matrix of 8 by 8 or 16 by 16 switches or 64 by 64 depending upon the requirement. Okay, so far we are doing this simulation work. However, now we have the fabrication facility that is coming up thanks to DST for the FIST facility that we are building here. Okay, so the conclusion is these devices, they are non-volatile, that's why they are promising they will consume less power. We have obtained the high performance at both the wavelengths. Okay, and it turns out that the reconfigurability because of the thermo-optic coefficient, which is high in case of amorphous, has the potential for fully reconfigurable circuits. So this I will not. So I would like to tell that we have integrated photonics research laboratory here. Okay, so we are doing terahertz photonics also along with this phase change based devices. We have generous funding from BRICS STI framework and also early career research award. We have quite some support from IIT Roorkee, and we have FIST level grant. Okay, so we are building quite an ecosystem for photonic devices. In fact, electronic photonic integration, I should say. Okay, so we have other colleagues who are working here. So this shows some of the pictures from my lab where we have very high-end equipment. Okay, so this is the computing facility. Okay, and here we have a chip measurement setup. We have state-of-the-art the lasers actually. So this can go from 1500 nanometer to 1600 nanometer. We have C-band, L-band, grid tunable, continuously. You can sweep those lasers. We have multi-channel power meters, etc. Everybody is welcome to use if you have some devices to test, or if you have even something to simulate. Please feel welcome. Okay. However, please mind that this is really a genuineness is required. If you are serious, then only please go for this kind of work. And then we have high-speed equipments where we have arbitrary waveform generator. So where we can generate a data up to 32 gigabit per second. And we have this setup here that you see. So this is a sampling scope where electrical bandwidth is up to 50 gigahertz, very high speed, and optical is around 33 gigahertz kind of. Okay, I cannot show everything, but this is some of the glimpse from here. Okay, so if you are not in Padi Garhwal, you are somewhere else. If you are not in Padi, for those people, we are located here in IIT Roorkee, which is very near to Dehradun, and from Delhi also we are not that far. Okay, now with the highways being available, you can reach very quickly to IIT. Okay, so thanks, and now I am willing to take as many questions as you may have.
Participants, would you like to ask some questions to sir? Yes, Anup Sri Joshi.
Good afternoon, sir.
Yeah, good afternoon.
Sir, my question is that if I want to observe the transmittance, absorbance, and a transmittance, reflectance, and absorbance property of GST on silicon or SiO2 substrate, so what should be the thickness of the GST that can be used to observe these characteristics?
So the thing is, if you are properly placing into the silicon, okay, let's say it is at the center, even
Yes,
10 to 50 nanometers is fine.
Okay, sir.
Yeah.
Okay.
If you deposit higher, then also you can do. Okay. With the higher, it is always possible. I mean, it is easy, but with the lower, it is difficult, right? But you can well align. So you have a silicon on insulator waveguide. If you can well align your fibers for the input and output. Okay. And if you have a few milliwatt of power, with that, you can basically see the reflection as well as the transmission, and absorption you can calculate because R plus T plus A equals to 1. Okay.
Yes, sir. Yes.
And also you can calculate mathematically. Now for the reflection, since this is less, okay, your power meter at the other side need to be very sensitive. Okay. So we have a power meter which can basically, detect even in picowatts. Okay. Now, if you cannot have that sensitive power meter, you can always have higher input power and you can see it back.
Okay, sir.
Yeah.
Okay, thank you so much, sir.
Anyone else? Participants? Yes. Please raise your hand and then ask the question. Participant, I think so. No one is interested to ask the question.
I think it is also because the final day and being online is also tiring some. I can understand for them. They are attending continuously. And also, it should be 1.5 hours, but I deliberately now moved faster so that the interest remains there. But please feel welcome. If you have any questions, you can also ask me later.
Yes, Anup, say.
Yes, sir. I will be grateful if I will get your mail ID or contact number.
Okay. So you can always get it from the organizers. And my
Okay.
email ID is always there on the website.
I think
Okay,
so,
sir.
Anup, you are doing PhD under Dr. Nathani, I think so. Am I
Yes, sir.
correct?
Yes, sir. Yes,
So
sir.
you
So,
you
so
you may take the contact number from him.
Okay,
yeah,
sir.
he
Okay, sir.
he knows he knows where I am located, what is my phone number, what is my email ID.
I think
So
so. Your one supervisor is also from IIT Roorkee, Professor Kaushik.
Kaushik, sir. Yes, sir.
Yeah.
so you can also ask Professor Brijesh Kaushik. He knows everything about me.
Okay,
Yeah.
sir. Thank you so much,
So
sir.
You may,
he knows where my office is. If you want to
Yes,
visit, where my lab is, if you want to do experiments, and
yes,
he definitely knows the email number and phone.
you
Sorry,
may
email
direct.
sure.
ID and phone number where you can talk to me. But I prefer
Okay,
first the emails.
okay, sir.
You,
Okay,
di-
sure.
you direct contact through Dr. Nathani or Professor Kaushik.
Yes, sir. Yes, sir. Thank you so much, sir.
Okay. Anyone else? Okay, sir. Thank you for wonderful lecture. I am also from the domain of devices.
Nice to hear that.
Yeah, I did my PhD from IIT BHU Varanasi
Mhm.
under the supervision of Professor Jeet.
Okay.
And yeah. Okay,
Okay,
sir.
that's nice. Okay, so yeah, thanks for organizing this and
Uh,
yeah,
Thank you.
for having me here and yeah, have a good time there.
Okay, okay. Thank you, sir. Hello, participants. I think so. There is the last session at 2:30 p.m. I think so. I don't know what is the exact time of the last session. That is the validatory session. Am I correct? Hmm? So you can send your feedback and say feedback and test. I think so. The link of the test is shared with you. I think so. And there is a validatory session at what is the timing of validatory session, sir? Thakkar sir? Uh, Let me check. What is the timing of validatory session?
It's 2:30, sir.
Okay,
Hello?
2:35. 2:30. Timing is 2:30.
Yes.
So and be present in the validatory session. It will be interesting. Your feedback is very, very important for the FDP so that we can improve the lacunas of the FDP in next FDP. Okay. So you are most welcome in the next section. Okay. So thank you. Thank you very much.